Hello and welcome again to my physics short video lectures. Today's video I want to talk a bit about viscosity and Poiseuille's law. Basically, this video is building on the previous video in fluid dynamics. In the previous one we considered an ideal fluid and looked at the conservation of mass and of energy via the continuity equation and via the Bernoulli's principle. Today's video we want to take a slightly more realistic fluid, and the way that we do that is by adding one property that fluids generally do have, which is viscosity. So in order to do that, we're going to have to consider what viscosity is, and then we're going to add to that the law that governs the motion of a viscous fluid through, say, a cylindrical tube, basically through a hose or pipe or tube. So let's get into it. First question that needs to be answered is, what is viscosity? All right, so a fluid is viscous if there is some amount of friction between layers. So in some sense, viscosity implies friction in a fluid, where it implies that there will be drag from the fluid. So friction in and therefore drag from a fluid. Basically, it's within a fluid itself, it's basically friction between different layers within the fluid. So let's say that I happen to have a large tank full of fluid like this. So this is sort of my tank of fluid. Maybe it's water, maybe it's some other fluid. And I decide to do something to drag one part of the fluid relative to the other. So if I do that, maybe I put something at the top of the fluid and drag it along the top. So maybe I have a little object just kind of floating along here near the surface, and I'm going to pull the object along like this. And so eventually my fluid has an object that has now been moved to the other side, and in doing so, this object kind of drags this fluid along this way, and the top layer kind of drags this way against the object. And so what I kind of get is just layers within that fluid in which each layer is dragging against the subsequent layer above or below it. So we could draw this represented by drawing a bunch of lines to represent different layers within the fluid. And what I would expect to have happen is that if I had a way to measure the speed at which a fluid is moving, say like this bit of fluid right here, I would expect it to have a relatively large speed compared to the fluid at the bottom, which is going to do this. And of course you have edging effects, so out here maybe you get a bit of turbulence. Back here maybe you also get a bit of turbulence because the fluid sort of like sloshes back and forth. But by and large, ignoring the turbulent effects, the farther down in the fluid you go, the less you expect the fluid to be disturbed by dragging something along the surface. And so by the time I get down maybe to the bottom layer, there may actually be no fluid motion. Okay, so the deeper the fluid is, the less disturbed these lower layers will be, is one key item here. So another one is that the larger the object up here that I'm dragging, larger object will basically mean more drag. We know that from our study in Physics 1 of drag forces. So in some sense, more friction or drag between the object and the layers of fluid that it's interacting with. And then also, the faster we drag the object, the more drag we get. Again, recall from Stokes' law, in Stokes' law drag earlier in physics, that the drag force Fd is given by some set of constants. Usually we use like a 6 pi eta, and then there's usually some length parameter and then some speed parameter. And this right here is your speed parameter. The faster we drag this, the larger this force is. This right here is your viscosity. And this right here is basically your length scale, or perhaps area scale, for your dragging force. All right, and for actual Stokes' law, you get these two parameters, and this length is actually a radius, because for Stokes' law we assume a spherical object that's being dragged. Here we have maybe a non-spherical object. So we can generalize it by having a length scale, and maybe these parameters change to some other number than 6. It depends on the geometry involved. All right, so if you put all of that together, what do you end up getting? Basically, what ends up happening is that for this object right here, for the amount of drag that's being placed on it, let's call this the drag force, the actual drag force, not a Stokes' law, but the actual drag force from the top layer of the fluid, you end up getting a force that looks like this. F is equal to eta times V times A over L, where this right here is basically your sort of cross-section area. So this is area of the plate or whatever object. So call it object, and e.g. like a plate. So like if you're dragging a plate across the top of water, then you'd have the plate itself is maybe like this oriented to the water, but if you looked at it from above, you'd maybe have something shaped like this. This right here would represent your area. So this area is this right here. Be that as it may, this right here is your viscosity term. This is the measurement of how much friction, if you will, the fluid has. And so we could solve this whole equation to get the value of eta. Essentially what you do is you drag this plate along the fluid at some constant speed v, so constant speed, and so all these others are also constants. You'd require a constant amount of force. You can solve for the viscosity, or the coefficient of viscosity, eta. Essentially it's going to be how much force is needed to drag this thing along the surface, or in other words, how much drag force is there being applied to it, times the length scale. In this case is basically how deep is the fluid, divided by your speed times your cross-section area. So again, from the side view, my fluid has some depth like this, and then down here is like the bottom of the container. Then this distance right here from top of the fluid to bottom of the fluid would be my length scale L. Alright, so this right here is what's called coefficient of viscosity, sometimes just viscosity. And then the unit, for what it's worth, is in Pascal seconds. So those are the correct SI units for viscosity. So before I go on to Poiseuille's theorem, let's consider a fairly brief example. So let's say that we have a fluid. Let's say that we've put a plate that's basically floating at the top of the fluid, and we want to drag some item through the fluid. And we're told how much force is there, we're told what the area is, we know what the depth is, and we know what the speed is, and basically we just want to know what is the value of the coefficient of viscosity. So to solve this, basically your coefficient of viscosity, eta, is again going to be the force that we're dragging with times the depth of the fluid, L, the length between the plate and the bottom of the fluid essentially, divided by the speed that you're dragging at times the cross-section area. So we plug in our numbers. We got 1.2 newtons here. We have a depth of 6 centimeters. That is the same as 0.060 meters. We want everything in meters, meters squared, that kind of thing. The speed, we're dragging at 2.3 meters per second. All right, and then the area, of course, is 25 square centimeters, so that's 25 times 10 to the minus 4 square meters. Remember that each 1 square centimeter is 10 to the minus 4 square meters. So this you plug into your calculator, and I'm going to use this calculator today. So 1.2 times 0.06 divided by 2.3 divided by 25 times basically 10 to the 4. And you end up getting a viscosity of 12.5. So this is actually a very viscous fluid for what it's worth. Your viscosity is about 12.5 Pascal seconds. And again, for what it's worth, there exists a table of viscosity values in your textbook to give some comparisons. Honey at 20 degrees C, depending upon the quality of the honey, has a value of between 2 and roughly 10 Pascal seconds. So for comparison's sake, honey has a value of roughly between 2 up to maybe 10 Pascal seconds at 20 degrees C, so at room temperature. So if you cooled honey down, the viscosity would maybe approach this value. So this is a very viscous substance. Maybe we're looking at like molasses or something like that. So this brings us to basically the flow of a viscous fluid through a tube or pipe or vein or whatever. And that is governed by what's called Poiseuille's theorem. So Poiseuille was basically actually originally interested in studying the flow of blood through somebody's veins and arteries. So this actually was originally looking into anatomy and physiology, and he did these studies, and basically what he came up with was this. First of all, it was known based on viscosity that if you have, let's say, a cylindrical vessel like this and you have fluid flowing through it, if it's not viscous, then there's no dragging between layers, and the result will largely be that every layer in the fluid will have the same rough flow speed. So this is not viscous. But if you have a tube, same properties, but now you have a fluid that is viscous flowing through it, then essentially the farther away from the walls, the faster the fluid should flow. So you end up with a velocity profile that maybe looks more like this. So as you get closer to the walls, there's more drag between fluid and wall, or maybe I should say the wall is stationary, and so you have a greater velocity difference that you're trying to force, and therefore you get more drag, and therefore a slower fluid. And then in the middle you have a greatest velocity. So this is your velocity profile. And this, for what it's worth, is the reason why when you have like a Bunsen burner or a flame coming out of a tube, it doesn't have a shape like this when it's flowing out. This isn't what the flame looks like. The flame usually looks more like this. It's basically because this part of it is moving faster and therefore makes it sort of farther along than these do when burning up. Okay, so what Poiseuille's law says is that for a viscous fluid, the volume flow rate, big Q, remember this is volume flow rate, volume per unit time, is going to be the pressure difference between basically the two ends of the tube divided by what's called the resistance of the tube to flow. So this is resistance of fluid and tube. So we'll call this resistance to flow. And again, that's a property of actually both the vessel, the tube, hose, pipe, whatever, and the fluid itself. It turns out that this resistance to flow is given by, for a cylindrical tube, 8 times the viscosity of the fluid times the length of the tube divided by pi times the radius to the 4th power of the tube. So if this is like one end of the tube and this is the other end, the length would be this distance right here from end to end. The radius would be the radius of the opening. So this is little r radius. This right here is little r radius, etc. And then eta is your viscosity of your fluid. Note that I've used the symbol little l twice in this, and they've had slightly different meanings for the two equations. But that is just how it is. They're both lengths. And then that basically means that in some sense we could rewrite Poiseuille's theorem. So Poiseuille's law says Q is delta P over R, which is, given how R is defined for a cylindrical tube, this becomes delta P times pi r to the 4th divided by 8 eta L. So this is Poiseuille's theorem in general. So Poiseuille in general. And then this one right here is Poiseuille's law for a cylindrical tube, or in other words, for a tube that has circular cross-section. Note, by the way, this r to the 4th power that is in this equation, that means that the resistance very strongly depends upon the size of the cross-section. It also means that the flow rate strongly depends on the size of the cross-section. Also, the delta P basically means you have some pressure here and you have some further pressure here, and the pressure here must be greater than the pressure here in order to push the viscous fluid through. This r to the 4th power term means that there's going to be a very strong dependence on the size of the aperture. So here's a quick biomedical application. If you have somebody whose blood vessels are starting to have plaque buildup, so maybe here are the walls of the vessel, and then we add to these walls a bit of plaque. So plaque builds up along the two walls, thereby constricting this. Your R has decreased by, let's say, 10% here, but a 10% decrease in R can be a pretty substantial increase in the resistance to flow. Now you need the same amount of fluid, basically of blood, to flow through here at any given time. So the result is that this pressure difference has to increase proportionately. So a 10% drop in the radius basically means your radius is 0.9 times what it was originally. Means you only get 65% as much flow for a given pressure. And so your blood pressure then needs to increase by a factor of almost 50%, like roughly 50% increase in your blood pressure to get the same amount of blood flowing through that same artery. All right, so let's close with a nice example here. So let's say that we have blood, it's flowing through an artery, the diameter of the artery is given, the pressure drop from one end to the other is known. This is at 80 millimeters mercury, and then we have a known length, and we want to know what is the volume flow rate of the blood. So we know that Q is equal to delta P times pi times r to the fourth divided by 8 eta L. Okay, so some of these numbers were given in the sentence. For example, delta P is 10,700 pascals. Okay, that's given right here. The pi, obviously pi is just 3.14, etc. R is given right here. In fact, this is D is equal to 2R, so R is equal to 1/2 of D. So this would be basically 2.5 times 10 to the minus 3, all divided by 2, quantity to the fourth power. And then we have 8, and then eta we'd have to go look up in a chart, and then L is 0.85 meters long. So if we were to go look up the value of the viscosity or coefficient of viscosity for blood, whole blood at 37 degrees C, that's basically normal body temperature, has a coefficient of viscosity of 2.08, roughly 4 millipascal seconds. So that's times 10 to the minus 3 pascal seconds. All right. So we now have to put everything into the calculator. So 10,700 times pi times 2.5 to the fourth power divided by 2 to the fourth power times 10 to the negative 3 then raised to the fourth power. That's like times 10 to the minus 12. Okay, and so that's everything in the numerator, and then we divide by 8, we divide by 0.85, and we divide by 2.084 times 10 to the minus 3. That gives us a volume flow rate of Q equals about 5.79. So maybe we have two significant figures, so we'll call that 5.8 times 10 to the negative 6. All right, and that is in cubic meters per second. For what it's worth, you could convert this into liters per second. So this ends up being 0.0058 liters per second. And that is the volume flow rate for this system. All right, so that's all that I'm going to cover in today's video. It is a little on the lengthy side, unfortunately, but that's in order to get both the topic of viscosity and the topic of Poiseuille's theorem in. It's going to be a little longer of a video by nature. So I've tried not to make too many of these that are noticeably more than 20 minutes long. This one, unfortunately, is a little over 20 minutes this time. So thank you for bearing with me, and hope you learned something from this video, and thanks for watching.